So our next speaker is Mirjam Cvetič, who will tell us about higher global symmetries from nesting of symmetry theories.
So I will report of some work in progress or about to appear relating to higher global symmetries in more complicated contexts, which would involve nesting of symmetry theories. As I mentioned, this is a work with a Penn group, Ron Donaghy, Jonathan Heckman, Max Hübner, and Ethan Torres, 3 of them here, as well as earlier work with 3 of them. So there were a number of talks on symmetry theories by Iñaki in particular, Jonathan and Ling. And so I will not go into too many details about the starting point of introduction of symmetry theories, but I will focus on a new perspective, namely the nesting of symmetry theories. So I have to apologize in advance for some unintentional misreferences. Yeah, I tried. Okay. So I would like to approach to the introduction of this nested symmetries, symmetry theories, first purely from quantum field theory. Okay. So when studying global symmetries in quantum field theories, the introduction of symmetry topological field theories is natural in the sense that in d dimensions we can often isolate symmetry structures into topological field theory in 1 dimension higher. So this is the notion of introducing symmetry topological field theory, where if we start addressing specifically the symmetry structure of QFT, there are physical boundary conditions on one edge in d dimensions, and then there is a symmetry TFT extending in 1 dimension higher, and typically ends with the boundary topological boundary conditions on the other edge, which are topological. Well, we can take perspective slightly, a different perspective slightly, by looking at this symmetry TFT in d plus 1 dimension, but get rid of edges, okay? So in this case, this looks just like d plus 1 dimensional quantum field theory, just effectively like the initial quantum field theory. So we can start addressing symmetry structure of this quantum field theory. So in particular, what is crucial that often, more often than not in recent times, it happens that this symmetry topological field theory is not necessarily topological field theory. In particular, that was observed by a number of authors when studying continuous global symmetries in d-dimension quantum field theory. Okay. So it's somehow natural then to study now the symmetry TFT and replace it now with the symmetry theory. And now we want to study further its global symmetry properties. So we can go on. Oops, we can go on now. I have a, okay. Maybe I can do it by hand. I like to actually just use the computer. Okay, so yeah, yeah, it's easier for me. Okay. Yeah, so let me do. Sorry for this. So as I said, right, we are starting now in d plus 1 dimension with the theory that is not necessarily topological field theory and return to the starting point of 1A step. So we can reiterate the procedure for this D+1 symmetry theory and construct one dimension higher symmetry theory to study the symmetries of this D+1 dimensional theory. Okay. So let me sketch these steps. So as I said, starting with symmetry theory in D+1 dimension, okay, we can naturally decompress it to study its symmetry structures into one dimension higher. But if we now recall that this D+1 symmetry theory had on one edge physical degrees of freedom of d-dimensional quantum field theory, this decompression takes a form of the edge physical d-dimensional quantum field theory that now spans two D+1 symmetry theories across D+2. So this is the essence of the nesting. And in principle, one can go on and continue with this nesting procedure. So this is from purely quantum field theory perspective. The idea, this idea is analogously motivated also by considering defects in say d-dimensional quantum field theories. So if we put a defect into this d-dimensional quantum field theory in small dimension d, smaller than capital D, right? We are dealing with this domain here of quantum field theory in capital D dimensions with the defect inserted in lower dimension small d. Okay. Now, if we want to, in particular, study this combined system from the point of view of symmetries, we can turn to compactifying this capital D dimensional field theory to D+1 dimensions, a la Kaluza-Klein, okay? And this defect theory now has its own symmetry theory in D+1 dimension here. So it sits, the defect theory now sits at the corner as the edge mode between this Kaluza-Klein reduced higher dimensional field theory and its own symmetry theory that it's associated with. And this goes across now D+2 dimensional symmetry theory. So as I said, this is very natural when we are dealing with the defects in quantum field theory. Okay? And the previous picture is related to that one, really by just rotating and deforming the previous picture and keeping this boundary on the other side, topological boundaries, loose. Okay, now let me turn to the point 3. Symmetry theories are very natural from string theory point of view, namely from the geometric engineering point of view. Okay. So the prototype example with isolated singularity would be a QFT at the tip of a cone, where cone is a non-compact particular cone that extends to infinity. We can introduce their defect operators, symmetry operators, and study via geometric engineering the global symmetry structure here. But if we take this radial cone size as an extra direction that specifies symmetry theory now, this is a natural way of relating the geometry here to the symmetry theory description in D+1 dimension along this radial slice. And this, again, this is a big industry. A lot of people working on this particular proposal within geometric engineering. All right. But I want to discuss within geometric engineering examples that lead to nesting of symmetry theories. And I'm going to just qualitatively describe a prototype example, which is the string theory description of intersecting branes on non-compact space. What we know is that in this case, we have field theories associated with this non-compact branes, flavor branes that intersect, and there is a defect degree of freedom at this intersection, which we know from string theory, okay? So we can geometrically describe, as I said, you know, this flavor branes that intersect at the star, defect field theory. We can excise the singularities and describe the tubular regions around the flavor branes and then glue those tubes in this neighborhood associated with this intersection. And so to get the whole tubular neighborhood of the full singular locus now, that includes also the intersection. Anyway, this example is very instructive in the spirit of nested symmetry theories. In particular, defect within quantum field theory description in terms of nested theory is obvious. So number 2 is obvious here. Okay? Connection to pure field theory description is taking now compactification down just to the radial slices of those intersecting d branes. That's describing d plus 1 dimensional Kaluza-Klein reduced intersecting brane field theory. Okay? And then the defect field theory is associated with this corner, and symmetry theory in d plus 1 dimension is associated actually geometrically with the excise boundary of this construction. But clearly what we have is in between, we are describing now the symmetry theory in d plus 2 dimensions. So those are sort of motivations from different perspectives. Now let me go and describe that in more specific, concrete example, which has few more technical details. And I will focus actually in this context of nested symmetry theories only on torsional case. And I'll conclude then with some remarks and outlook. So the prototype in which I'm going to more concretely describe this phenomenon is a description of 5D CFT, which in string theory would be M theory compactified on, not compactified, M theory on non-compact 3-dimensional orbifold, or six-dimensional orbifold, so, but the non-compact version of it, okay? So this is a particular non-compact Z2N orbifold, where we have at the tip of the cone description, the one way of describing this field theory from the geometric engineering point of view is at the tip of the cone, we have 5-dimensional SCFT. And then in this particular case, we also have a flavor brane that extends to the infinity, so, and sits in codimension 4. There is also equivalent description in terms of vibration over one complex coordinate, which traces the brane and traces the CFT part of the field theory. So we are dealing in this case with 5D SCFT, and now also with SU2 flavor brane in this case, which now lives in 2 dimensions higher because of the extension of this codimension 4 a non-compact locus. So effectively what we are describing in this context is SU and 5D CFT as a defect in 7D SU2 super Yang-Mills theory. Okay. Well, this example was actually studied a few years ago, where we actually used the algebraic topology to study the higher form global symmetries, in particular discovering on top of 0 and 1 form also 2-group structure. in this case. So what is this new perspective giving us? Okay. So first of all, within the current framework, we are having a concrete construction of the nested symmetry theory of this joint 7D, 5D system. Yes, it will reproduce some of the old results, but the framework is now more general, as one can now study any topological operator and their behaviors within this nested symmetry theories. And in particular, what we are most interested in is how these topological operators in the bulk of this 7D theory are pushed onto the boundary, 5D symmetry boundary. Furthermore, we have better insights also into studying more involved topological terms and so on. I hope I can mention a few things. So how much time do I have? 15 minutes? 15? 5? 7? Okay. Well, in any case, let me just speed up a bit. So because the whole thing was to emphasize the new perspective in this context. And so what we are doing, this is clearly, now dealing with this prescription of nesting symmetry theories. In this context, we have this 5D CFT, where we compactify in this extra dimension along the circles where the flavor brane sits, and that will lead us to the 6D Kaluza-Klein reduced flavor field theory. And at this edge, we still have 5D SCFT. Now, the whole effort is to construct the full symmetry theory from the normal geometry, both of this compactified flavor brane part and the CFT part. So this, in principle, could be done by studying topological 11th supergravity and reducing then the corresponding fields to the effective theory associated now with this first 7D symmetry theory, and also understanding the boundary 6D symmetry theory. Right. So as I said, bulk flavor branes are associated with 7D CMT and edge mode with 6D CFT, and then of course we have the corner mode here at the where the final story about 5D CFT is taking place. In any case, so let me talk about specific example now about properties of this nested CFT. Symmetry theory. In particular, let me focus on this particular example of one form, torsional symmetries that are actually backgrounds for 6D SU2 Kaluza-Klein flavor symmetry, and also for 5Ds superconformal field theory. Okay? And they are being actually described in theory by the two forum or two co-cycles, which are mod Z2 in 7D sim theory and mod Z2N in the corresponding boundary edge sim theory. Okay. And so what is crucial here now, we have interplay of the higher dimensional nested field theory and the boundary edge one, and there are boundary conditions between these two co-cycles. In particular, the bulk ones on the right edge have to satisfy this boundary condition relative to those in the edge symmetry theory. And that produces for us actually in the edge symmetry theory only the n worth of profiles that are not fixed, because the rest is fixed by that. And this produces now the concrete one-form symmetry to be Zn in 5D SCFT. And it's obtained from these boundary conditions between bulk and boundary theory. So we can see that the symmetry structure of the corner modes are those, of course, of the edge 6D CMT. But There's edge modes, edge symmetry CFT, edge symmetry theory, okay, is still constrained modulo boundary conditions to this bulk 7D SymTH. And it's actually this, in this picture, we see that the one-form symmetry of conformal field theory is extended by the one-form symmetry of the flavor branes. And in this case, we see the appearance of the two groups. So again, we have also both now, again, interpretation, what happens as the bulk symmetry theory hits the 6D edge symmetry theory, both from the field theory perspective and geometry perspective. But pictures should say 1,000 words. And for the sake of time, let me continue and just point out that, you know, I glossed over many things. I just highlighted some key points that we can obtain in this perspective. But in principle, we could derive the symmetry, the full symmetry theory Lagrangians. And in particular, we could focus on characterizing now new anomaly couplings in this case. So this framework actually already offers new interesting insights. In particular, we identified a new mixed anomaly of the flavor one-form symmetry associated with disco homologies and CFT ones. Sorry, this is one flavor. This is one-form flavor, and those are the CFT one-form symmetry. And there is a refined triple linking there that has to end up in multiples of 1 over n. And also, we have also the full pure one-form self-anomaly restricted with the pure 5D one-forms, and that also has a refined linking linkings that had to end up in multiples of 2 over n. So let me conclude. As I said, I gave you some initial insights in how much a new perspective that we can gain from nesting symmetry theories in more complex examples, and showed geometric engineering examples in this context. But there is a lot of things that have to be done, even in examples I'm showing here. In particular, we are involved in refined calculation of mixed anomalies, really getting the whole prefactors correctly in these calculations. Of course, more examples, higher order nesting, and so on. There is another important question that I just glossed over, which is the symmetry inheritance, how we relate defects and symmetry operators in the bulk symmetry theory to the boundary ones, which is at the end crucial for us. And I would also want to mention interesting perspective also that in this context of nested symmetry theories, we could potentially address lower form symmetries as well. In particular, again, prototype, if we have a defect in D dimensions in quantum field theory in capital D dimensions, we can introduce -1 form symmetry in this higher dimensional field theory that fills out the, whose operator fills out the whole space-time. But what happens when we constrain this -1 symmetry onto the defect? And we expect, in this case now, that this would give us quantum field theory on the defect that would yield even lower form symmetries inherited from this -1 symmetry. Of course, there are lots of detailed questions to be studied here. It could in principle be applied to any defect, quantum field theories, but how this process is invariantly defined is the lower depth in this procedure or so on. So that's separate. And in the last 30 seconds, the last outlook that I have, but not the least, is the fate of global symmetries on the compact models. Those examples that I showed you were global symmetries, and now I want to compactify these models and how to relate these issues of global symmetries with the singular strata of, in varying dimensions in these compact spaces. So actually, we've done this compactification via gluing and cutting already in 4-dimensional and some 6-dimensional examples, and traced through direct process of cutting and gluing what is the fate of specific global symmetries, whether they are broken or whether they become gauged. Right? And here we naturally, if we have just localized singularities at the tips of those cones and we glue them, that naturally leads us to describing the symmetry theory where there is some junction inside this compact Calabi-Yau space, and in this sim theory, it's expected that this junction is both has both topological and non-topological degrees of freedom, and that initial steps in this context have already been addressed in these papers, and leads to the symmetry trees. What is interesting now is really the harder question, which is inclusion of flavor brains in this context and studying the strata of singularities, which would systematize this gluing procedure and leading to nesting sim trees. We touch a little bit of that for some 6-dimensional examples, but the higher strata singularity was squeezed in one conical non-compact case. But we want to do that systematically, and this should be possible now with this perspective of nesting, in this case, sim trees. Thank you.